Welcome to our video on our introduction on how to use the ESM3 model in Python. In this video, I will give you a beginner-friendly guide to getting started with ESM3. First, we will go through installation and setup, and then we will look at a few example applications. This won't be a complete list of everything that you can do with the model, but it should give you a solid introduction. If you have specific applications in mind that aren't covered here, feel free to leave a comment below the video and we may cover them in a future tutorial. All the code that you see in this video, along with the data that we use, is available on our GitHub page. The link is in the video description. In this notebook, we will cover three use cases. First, protein engineering. More specifically, given a protein, we will predict suitable amino acid substitutions at specific positions. This means we predict substitutions that ESM3 considers plausible. Then we will look at how ESM3 can help predict the function of a protein. And finally, we will predict a 3D structure from a sequence and export it as a PDB file. In other words, we will show you how to go from sequence to structure. Before we begin, there's one important licensing detail. The smaller openly released ESM3 model used in this video is published under the Cambrian non-commercial license. This means you can freely use it for typical academic purposes, including publishing results in academic papers. However, you cannot use ESM3 outputs for commercial applications without an additional commercial agreement. Before we look at the applications, let's go through the setup. In the README on the GitHub page, you will find instructions for creating the correct environment. I created an environment file containing all required packages, so just follow the README. After installing and activating the environment, you will need to accept the ESM3 license on Hugging Face. That means you need to create or use a Hugging Face account, then open the link provided here and accept the licensing details or terms. Then create an access token with read permissions by clicking on this link. And finally, you need to log into Hugging Face using this code snippet here by entering your access token. Make sure you don't make your access token public. That's why I've removed mine here. You only need to do this once before downloading the model for the first time. Next, we will check if everything works. We import the required packages. We load the model. Loading it for the first time will take a while because it downloads the weights. Later runs will be much faster. And then we inspect the model tokenizers. ESM3 can process sequence tokens, structure tokens, and functional tokens. At each position in the amino acid sequence, we can encode the amino acid identity as a sequence token. We can encode the local 3D structure environment as a structure token, or we can also encode function-related information. We will look at that later in more detail. As the input of ESM3, you can provide between 1 and 3 of those token types. The vocabulary sizes are 33 for the amino acid or sequence vocabulary. This is the same as for the ESM2 sequence-only transformer. We have tokens for the standard amino acids, plus a few special tokens as you see below. If you want to know more about ESM2, we've also published a video explaining how ESM2 works and another on how to use ESM2 in Python. Both links are provided in the video description. Then we have 4101 structure tokens encoding local atomic structure environments per amino acid. This can be generated automatically when you provide a protein PDB structure. And then we also have 260 function tokens. Now we will prepare a protein as the input for our model. Here I copied the protein sequence that we want to use. Strictly speaking, we don't need a raw sequence because we will load a PDB file as model input, which also contains sequence information. But it's useful to keep it around so we know which amino acids we are dealing with. This example protein has UniProt ID Q8K1F9. It's a lactase enzyme, meaning it splits the milk sugar lactose into glucose and galactose. Humans also produce the enzyme lactase. And people who are lactose intolerant typically don't produce enough of it, so they can't digest lactose without adding lactase. I downloaded the corresponding structure for this protein from AlphaFold and saved the PDB file in the data folder. Next, we create an ESM-protein object directly from the PDB file. That's very straightforward, and then we can inspect it. The protein sequence has a length of 566. You can check the first 10 amino acids match the sequence we copied earlier. There are no functional annotations, which makes sense because the PDB file doesn't contain function labels. And we have structure coordinates with shape 566, 37, and 3. 566 is the sequence length with 566 amino acids. At each position, we have a tensor of dimension 37 times 3. We have 3 spatial dimensions for the x, y, and z coordinates, and we can store up to 37 coordinates per amino acids. If we inspect, for example, position 0, we see the atom coordinates. You can compare these values to the PDB file, and you will see that they match the atom coordinates of the methionine at the first position. The earlier coordinates correspond to the backbone atoms, and later ones correspond to the side chain atoms. Now we tokenize the protein, so we can use it as the input for the ESM3 model. This is also simple. We can take the protein object and call model.encode. Then we can inspect the tokens that are created. Here I printed the sequence tokens, which look similar to what we would expect from a sequence transformer like ESM2. The 0 at the beginning is the classification token, and at the very end we would see an end of sequence token. So in total we have 568 sequence tokens. Similarly, for every position in the sequence we also have a structure token that encodes the local 3D environment of each amino acid. Now we want to make a prediction. Which amino acids are suitable at each position of the sequence? For now, we will compute predictions for all positions and then focus on one specific position. We simply call model.forward, provide the sequence and structure tokens, and then expect the sequence logits, which are the model's predictions for amino acids at each position. The sequence logits have shape 568 times 64. Even though we only have 33 sequence or amino acid tokens, the output dimension is 64. I've read somewhere that this is likely done for efficiency by padding to the next power of 2, so we can ignore all logits after index 33. These are raw logits, so we need to convert them into probabilities by applying the softmax function along the last dimension. This gives us, at every position, a probability distribution over the amino acid tokens. Now let's say we want to engineer the protein and substitute the amino acid at position 100, for example to improve stability, efficiency, or some other property. We want to identify candidate substitutions that ESM3 considers plausible at that site. Here we extract predictions for position 100. Since indexing is 0-based, that corresponds to position 101 in a 1-based numbering scheme. We print the true amino acid at that position, which is E. Then we iterate through the vocabulary, take all amino acid letters and print their predicted probabilities at that position. In this example we see E has the highest probability at 53%, D is next at 21%, and Q follows at 9%. So D or Q could be reasonable substitution candidates, likely to still produce a protein that folds properly and remain or retain the function. And we could test experimentally if these substitutions even improve some properties. Of course, we can repeat this analysis for every position in the sequence. One important thing to consider is, since we did not mask any positions, especially not position 100, this prediction is biased towards the true amino acid, because the model already saw it in the input. If you want a less biased estimate, you can modify the input sequence tokens as follows. Look up the token ID for the masking token, replace the token at the position you want to evaluate with the masked token ID, and run the forward pass again. Then you will get a much less biased prediction for that position. This is the basic workflow for generating amino acid substitution suggestions and estimating how plausible different substitutions are. You can also extend this approach You could mask a larger fragment to predict replacements for whole segments, or even generate an entirely new sequence conditioned on structure. But we won't cover these applications in this video. If you would like to see topics like that, leave a comment below and we may make a video or a follow-up video on this. Now let's have a look at how we can use ESM3 to predict the function of a protein. We can reuse the same output we have generated above, but this time we won't look at the sequence logits, but we will look at the functional logits. First, let's check the shape. We again have a leading dimension of 1 because our batch size is 1. Then we have 568 positions because the protein has 566 amino acids plus the 2 special tokens at the beginning and the end. Finally, at each position we have a tensor of shape 8 times 260. That means for every position the model produces 8 function predictions, each over a function vocabulary of size 260. Next, we take the most likely function prediction. We apply the argmax function to the functional logits, which gives us a tensor of shape 568 times 8. Now we can use the ESM package decode function annotations function with the predicted logit tokens as the input to obtain predicted functional labels. You will see functional labels like these. Some of them look like fragments of longer annotations, and I'm not entirely sure why they appear that way, but overall the predictions are consistent. For example, one of the labels is glycoside hydrolase, and several others point in the same direction. Glycosides are molecules that contain a sugar unit linked to another group via a glycosidic bond. And glycoside hydrolases are enzymes that split glycosidic bonds by using water. That fits well here because lactase cleaves the glycosidic bond in lactose, producing glucose and galactose. So while the prediction isn't specific enough to tell us exactly which sugar molecule or sugar substrate the enzyme acts on, it does correctly place the protein into the right functional class, a hydrolase acting on sugar-related bonds. Finally, let's look at how we can use ESM3 to predict a protein structure starting from its sequence. We again create a protein object, but this time not from the PDB file. Instead, we provide the amino acid sequence of our lactase enzyme. Then we call generate to generate a structure from the sequence. The num steps parameter controls how many refinement iterations we run. In general, more steps should lead to a better predicted structure. After generation, we save the results to a PDB file. One important detail is the generated PDB contains carbon and nitrogen backbone atoms only, not a full atom model with complete side chain atoms. So if you compare it to the original PDB we loaded earlier, you will see far fewer atoms. To reconstruct the full atom structure, we can use tools like PDB Fixer and OpenMM, which I've included in the environment file. We take the backbone-only PDB predicted by ESM3, run it through PDB Fixer to add missing atoms, and save the output as a new PDB file. If you open that file, you will see it now contains a complete structure. And if we want to further improve it, we can also use PDB Fixer to perform energy minimization on the completed structure. Because proteins typically adopt conformations that are close to an energy minimum, running an energy minimization step can help improve or remove unrealistic bond length, angles, or steric clashes introduced during reconstruction. It doesn't guarantee a more correct fold, but it often produces a more physically plausible structure. With that, you should have a good starting point for working with the ESM3 package in Python. As mentioned, we didn't cover every possible application, but if there are other use cases you would like to see, let us know.